Good morning.
Good morning, sir.
Yeah, so welcome back to another session on image processing. I think we had a gap because of the first test. Um, Let me just quickly refresh what we did in the previous class because there is a gap. Then I think we will go ahead with the discussions on the rest of the topics. Is my slides visible?
Yes, sir.
Yeah, okay. So we actually started discussions on image enhancement. We understood that there are two ways of doing it, one in spatial domain, other in frequency domain. And the basic objective here is to improve the image for the result to be more suitable compared to the original image. Um, uh, while doing it in spatial domain, we use maybe the uh, mask of a specific size and move this mask all across the image. So we are going to operate the pixels directly. That's why it's called spatial domain operation. And this mask can be of any size. It can be even one by one cross one also. If it is a mask of one cross one, then we call it as point processing. A very simple point processing technique is thresholding that we normally use to convert a gray color image into a binary image. So I think this you have understood. So these are some of the typical intensity transformation functions that uh, are basically used. What we saw is the first one is image negative, and image negative is going to convert a maybe a gray value by just subtracting the original value from the maximum. So, for example, if it is an 8-bit image, then L minus 1 will be 255. So 255 minus of the input value will be the output gray level. So obviously the dark pixels will become white and white pixels will become black. One of the very good application of this image negative is in medical image processing. Of course, even in text processing also, if you remember the on-ramp course that you did, while detecting the text, this negative operation was used. So, for example, this is actually a, an image, a medical image, where you could see some white patch here, which is surrounded by dominating dark region. So, in such cases, if I convert it into negative, this white region will look dark and the rest of the region looks white. So it is easy to locate the probably the image here, and a doctor would definitely get a better analysis of this type of images. So this is what we discussed in the last class, and also I think uh, we just took an example. Hope is the OneNote visible?
Yes, sir.
Okay, so I just took a 4-bit image. 4-bit image means you will have the maximum gray level as 16, 0 to 15. So these are the values of the pixels, and I took a simple image 4 cross 4. Suppose if such an image, if I just use an operation like this, okay, so it's here. So this is the 4-bit image, and if I use a negative operation like this, when I convert it into negative, this is what I'm going to get. That means 0 will be mapped as 15, etc. So this is how image negative operation is performed on a given image. Okay, moving on. The next operation is power law transformation. Logarithmic transformation. So as the name itself says, I am going to use log function to convert the input gray level into an output value. And this is the formula that is normally used for finding the logarithmic transformation. and I have already told you the importance of 1. Can somebody tell me what is the reason I add 1 to the input gray level? Can somebody unmute and just share this information?
Sir, log 1, if R is equal to 1, we can't use directly, so we will add plus 1.
Uh,
Log 0 is not dependent,
yes,
sir,
yes,
so
yes.
we need.
Correct, correct. Very good. If R is 0, then log 0 is a problem. That is why we add 1. And you know that 255 or 256, there is hardly any difference in terms of the gray level or the color of the image. So just adding 1 will not change the input much. So that is why, to take care of the log 0 problem, we just add 1. And this constant is used to convert the input values into a specific output range. If you observe carefully the plot, this is a logarithmic plot. So when the input has a specific input range, see, the maximum input gray level should reach a maximum gray level. Let me just explain this with an example. I'll just go to my OneNote. Okay. So what we do here is, I'll just take only the logarithmic transformation. So the curve is, as you know, this is the input gray level R and the output gray level S. Okay, this is in fact C into logarithm of 1 plus R. This is the formula that I'm going to use. So what happens is, logarithmic transformation looks something like this. So this is the curve. So what you notice is a very narrow range of input gray levels, if you carefully observe. So this is a very narrow range. So narrow range of dark pixels will map to a wide range of white pixels. Just observe that. Okay, a very narrow range here. Okay, and when I come to this region, I think there is a small slope here. So when I come to this region, a very wide range in the input value will map to a very narrow range here. This is a very narrow range. I hope you can visualize it easily. So that is exactly what I have written here. Maps a narrow range values to a wide range, and opposite is true for higher values of input levels. So uh, that is what is happening in the curve, a very narrow range. Okay, so a narrow range is mapped to wide range here, and a wide range of input values in the brighter side will be mapped to narrow range. Now, where is it being used is, I already have told you, if I want to plot the Fourier transform of an image. Okay, all of you know the formula that is used for finding the Fourier transform. In the last module we have discussed about it. So suppose if I just represent uh, f of uv as the Fourier representation of an image, the formula that is used is double summation x is equal to 0 to m minus 1, y is equal to 0 to n minus 1, f of x comma y e to the power of minus j 2 pi ux by m plus vy by n. Okay, I hope you remember this formula. This is a formula. Of course, the scale factor can be different, but it's okay. Now, if u is equal to v is equal to 0, that means I'm trying to calculate the zero frequency component of the image. What you will get is f of 0, 0 will be summation x and y f of x comma y. So when u is 0, v is 0, this term will be equal to 1. For u equal to 0, v is equal to 0. So since this term is 1, f of 0, 0 is so much. So if you observe carefully, it is summation of all the gray levels for all the values of x and y. Okay, so you can imagine if it is a say 1024 cross 1024 image, and assume that it is an 8-bit image, so the values are from 0 to 255. So if I add all the gray levels of a 1024 cross 1024 image, this value will be a huge number. This will be a huge number. Okay, I can demonstrate this a little while from now, but it's okay. So this is a huge number. So what happens is, if I want to display the spectrum of an image, that means display the Fourier transform of an image as an image. Let me write it. To display, should understand the concept clearly. To display Fourier transform of an image, that means I'll take an image and take its Fourier transform using this formula and display this as an image. So what happens is, the range will be, that means in your input values, once I take the Fourier transform, will be from 0 minimum to a very large value. In fact, usually it will be somewhere around 30 into 10 to the power of 6. This is the value. Now when I ask the when I want to display this as an image, what happens? All of you know that this maximum value will be shown as white, and the minimum value should be shown as black. So you can see 30 into 10 to the power of 6 will be displayed as white, and any values other than that will be displayed accordingly, and 0 will be black. So since this is very high compared to the other values in an image, if I show it as an image, then I'll only see a very small white dot on the image. Let me just show this with a MATLAB simulation. Okay, so what I have done here is, I have just read Lena image here. Don't worry about this. This is for something else. Don't worry. So I have read Lena image. I am just showing it. I am taking Fourier transform of Lena image. So Fourier transform of a two-dimensional data is done by using FFT2. Is the MATLAB window visible?
Yes, sir.
Yes,
Yes.
sir.
Okay. Okay. So I'll take Fourier transform of the image, and we use another command called FFT shift. Okay. Why this is done? Because normally, I think, let me just explain that also. So when I take an image, assume that this is an image, and I take its Fourier spectrum. All of you know, image means your 0 0 will be here, and the maximum will be here, say something like m minus 1, n minus 1. So this is the image, this is the spectrum. So in spectrum also, this will be your 0 frequency. So normally, just to see it better, the 0 frequency should be shifted to the center. Okay, so I need to shift it to the center, for which we use a command called FFT shift, which will actually move the 0 frequency component to the center. So when I display it, the center will be of 0 frequency, and as I move away from the center, I am going to the higher frequency. That is the reason why FFT shift is used for showing it. So I have just shifted that. I have used FFT shift. In fact, this FFT shift operation is exactly one of the property that I explained in the previous chapter. Okay, which will that means when you shift in the frequency domain, you know what happens in the spatial domain. So you multiply it with some exponential term. Anyway, so then I am taking absolute value because I want to display the magnitude spectrum. I want to show the mesh plot so that you will see the values, and then okay, I also want to show you what will be the maximum value. So let me just run this up to displaying the maximum value. Okay, so I'll not run the rest of the thing. The rest we will do it later. So if I evaluate this, now carefully observe this. Uh, uh, this is a mesh plot. Let me just show you the value on the. Okay, so do you see that number 30? This is the maximum value 32519084, which is exactly what I was telling you. This value. So 3 to such a large value is displayed. Such a large value is displayed as an image. So obviously the mesh plot will show you a very large value. Observe this. So observe, you have a very large value at the center. All other values are very small. They are almost minimal. Now if I show this as an image, if I show this as an image, what do you see? Can somebody comment? What is it you are seeing on the window? Can somebody comment? Anybody? Shivam, are you there?
Yes, sir.
Yeah, so do it.
Uh,
Okay, I'll just slightly zoom it. Okay, do you see something now?
Yes, sir.
What is it you are seeing?
The small
Yeah,
white dot
white dot
center.
is seen at the center because this is a very high value. That means it corresponds to this peak. The other neighboring values are very, very small. That is why you are seeing the rest of the thing black. So if I just directly display the Fourier transform of an image as an image, this is what you see. That means the dominating DC frequency value will be seen as white and all other values are seen dark, which indicates that the image has got only DC frequency and it is not having the other low frequency components, which is not true. Image will be definitely having other low frequency components also. In fact, it has edges also. So to take care of this, so what is happening? The input range is something like 0 to 30 into 10 to the power of 6. So what I need is these dark values that you see, somewhere here near this should be magnified, and this white value, this should be compressed. So the best in fact transformation could be this, because the dark values will be magnified and the white values will be compressed to the narrow range. So now what I do is I will try to use the formula S is equal to C into log of 1 plus R. Okay, now you already know why 1 is used. Okay, whenever R is 0, log 1 will take care of it. So log 0 problem is solved. Now I need to calculate the constant. So you know that the maximum value of R should map to the maximum value of the image. So R max should map to the maximum value. Let me assume that I want to display it as an 8-bit image. So what will be the maximum value if it is an 8-bit image? What will be the maximum value if it is an 8-bit image?
256.
255. Okay, 255 will be the maximum gray level. So to do this, I need to calculate the constant. So I can calculate the constant C equal to 255, because I want to display it as an 8-bit image, divided by log of 1 plus maximum value of R. Okay, now in this case, I have given R as the maximum value of R as 30 into 10 power 6. So it is 255 divided by log of 1 plus 30 into 10 power 6. So if somebody has a calculator with you, please tell me what is this constant value. Can somebody tell me the value?
Sir, 34.104.
34. Okay, so so if I choose C equal to 34, then 30 into 10 power 6 will take a value y 255. So this is how I'll calculate the constant. Okay, now let me demonstrate this by using the simulation here. Now if you observe carefully here, what I have done is I have taken maximum, well, this is a command to find the maximum value of a matrix. Max of y1 is r max. So 255 divided by log of 1 plus r max. That is exactly the formula I wrote. 255 divided by log of 1 plus r max. So I'm just calculating it. And I am just using logarithmic transformation. See, C into log of 1 plus the input gray level. So this is C into log of 1 plus R. So let me run this together, all of this, and demonstrate what has happened. So do you see the changes now? Now this is the Fourier transform. Earlier you were seeing it as a white dot like this. That was because this is dominating when compared to the neighboring values. Now I have used logarithmic transformation. You can see that the center pixel value, that white value has okay, is reduced to 255, and the neighboring values, small values, are enhanced. Okay, so narrow range of dark pixels are enhanced, and wide range of white pixels are compressed. So you could see more information in this image. What you should notice is, if I see a dominating line like this, it means that when I move along this line, the frequency variation is maximum. When I move along this line, the frequency variation is maximum. When I move along this line, the frequency is maximum. That's what it means. Okay, so this is what Fourier transform actually displays. So I hope you have understood the concept of logarithmic transformation. Any doubt? So
No, sir.
the equation is this, and please remember, when I ask you only logarithmic transformation, write only this curve. Don't write all the curves. Okay, this is given together, so I expect you to in fact show only this curve and explain. Okay, so because you are asked only logarithmic transformation, and you know how to calculate the constant also, and the application, as I told, the application is showing Fourier transform of an image as an image. So this is a place where you need some non-linear transformation like logarithmic transformation to compress the higher values and to expand the lower values. Okay, so this is about log transformation. Next one is what is known as power law transformation. As the name itself says, you are raising the input gray value to a power gamma, and of course multiplying with a constant, and again this constant is used to, okay, map the highest value of the input to 255. That means the whatever higher value you get. If it is an 8-bit image, it is 255. So now let us just try to plot some of these curves. Okay, in this plot, please remember this. Okay, even though it is given as L by 4, L by 2, 3, L by 4, and L minus 1, actually to explain this, the input value is normalized. So this is actually 0 to 1. Okay, so if I use 0 to 1 representation, then this will be probably 0.25, this is 0.5, this is 0.75, and this is 1. Similarly, this 0.25, 0.5, 0.751. Okay, so the values are normalized. For example, 0 to 255, if I want to normalize, you divide all through by 255, so I'll get 0 to 1. So the graph here is given for the value 0 to 1. How is it? Let us just try to understand it. So let me just now try to explain you power law transformation. So as I said, S is equal to C into R to the power of gamma for our case, let me just take C equal to 1. Say gamma is equal to say some 0.5. Okay, so we will plot this. So the input gray level, as I told, R has to take the values from 0 to 1. So I'll just take 0, 0.1, 0.2, etc. 1. Okay, and we need to calculate S accordingly. So this is only to show you how to calculate these values. So when the input value is 0, the output will be 0 because uh, constant C is 1, uh, gamma is 0.5, R is 0, so 0 to the power of anything is 0. Now if the input value is 0.1, what will be this value?
0.93, sir.
1.1 to the power of 0.5, how much is it?
0.93.
0.93 is it?
Yes, sir.
Okay. Mm, I doubt. Just check once again.
Sir, 0.316.
0.316. 0.5, sorry, 0.1 to the power of 0.5. Yeah, 0.316 is correct.
Yes, sir. 0.316.
Okay, what 0.2 to the power of 0.5? 0.2 to the power of 0.5. Quick.
0.44.
Yeah, 0.44.
0.44, sir.
Okay. Then the last one, 1 to the power of 0.5 is 1. Correct? Huh?
Yes, sir.
Okay. Now if I plot this, on the curve, so 0 is 0, 0.1 has taken 0.316, 0.2 has taken 0.44 and etc. So the curve will be something like this. Okay, so this is for 1, the output is 1. This is a maximum. Okay, now recalculate the same thing for gamma equal to 1.5 or gamma equal to 2. Okay, I want you to calculate it for gamma equal to 2. This is for gamma is equal to 0.5. Now I want it for gamma is equal to 2. Gamma is equal to 2. So what will you get? I want S value. R value is same. S value for gamma equal to 2. This is 0. 0.1 to the power of 2 is how much? Point?
0.01.
Yes, correct. 0.2 to the power of 2. 0.04, correct?
Yes, sir.
Correct, no? Yeah.
Yes.
So now if you plot this second curve, this is for gamma equal to 0.5. For gamma equal to 2, what do you notice? It will be something like this, correct? See, for 0.1 the value is 0.01. So for 0.1 the value is 0.01. For 0.2 the value is 0.04. So actually the curve is like this. So if I take this as a 45-degree line, that means when gamma is equal to 1, this is what happens. This is for gamma equal to 1. This is for gamma equal to 2. So what do you notice? When gamma is less than 1, the curve goes up. When gamma is greater than 1, the curve goes down. Carefully observe. Carefully observe here. So when gamma is less than 1, the curve is going upwards. When gamma is greater than 1, the curve is going downwards. See, same thing is not true if your values are from 0 to 255. This is a homework for you. You can verify it later. If the value input range is in the range of 0 to 255, you will actually get the reverse of this. Okay, that means for gamma less than 1, the curve will go down. For gamma greater than 1, the curve will go up. That is why I want you to be very careful. This is in the range 0 to 1. This is in the, that means normalized values are shown here. I hope the point is clear. Now, If this is the case, if this is the case, suppose if gamma is greater than, sorry, less than 1, what will happen to the image? Can somebody tell me? Looking at the curve, for example, this case, gamma equal to 0.4, what happens to the curve? Sorry, what happens to the image? What is that you are trying to do? Observe carefully, gamma is zero point 0.4, so observe dark values are brightened. Do you notice that? Dark values are brightened. Suppose if gamma is say 2.5, notice here that even brighter values are darkened because for a larger value of the input, the output gray value is less. Okay, so suppose if I have a very dark image, assume that I have captured an image at low light condition, or maybe the light intensity is very small, or maybe somewhere in the evening. I want to brighten an image. You have to choose gamma less than 1. Again, I repeat, this is only when I normalize the values. Don't forget that. Okay. So, by choosing the gamma carefully, I can either brighten an image or darken an image. Okay. So, where do we use it? Very good application is in what is known as um, gamma correction. This is a good example for that. All of you would have seen in your seminar halls in the EC block. Sometimes the display device, that means the projector, will show the images. Okay, sometimes darker. I hope you would have noticed it. Maybe due to continuous use of this LCD projectors, you may expect that the brightness is reduced. So to correct for that, we can use an image transformation, that is power law transformation. Okay. Now assume that I have an image of this nature. This is called a linear wedge image. What you see is here the brightness is 0. Here the brightness is 255. So linearly the brightness is increasing from 0 to 255. The value is increasing from, that is why you could see that it looks as if from when I move from left to right, the brightness is increasing and it reaches maximum. This is just like a ramp. Now suppose if I have a maybe a display device, it could be a monitor or it could be your LCD projector, which will introduce this type of transformation. Okay, what is happening? You can observe here that it is darkening the image. Do you see, when I go below this line, it is darkening. Okay, observe the right hand side. So this problem is because of the monitor or because of the display device that you have, maybe an LCD projector. Because it is trying to darken the image, I may get like this. Okay, now what we can do is, before actually giving it to the monitor, I will just pass such an image through a gamma correction and do an inverse of this operation. If it is doing like this, if the display device is doing like this, I'll do an opposite of it. That means instead of gamma, I'll take 1 by gamma and use a power law transformation. So I have brightened it, and now I will pass it through the monitor or the display device. Since I have increased or I have brightened it, even though it is trying to darken it, I'll get back the image which is same as this. Okay, so let me just explain this with a simple equation. Assume that I have a monitor. This is a monitor. So whatever input image I give, for example, I give it as R. Let us assume that it is trying to darken it, and we have seen that a larger value of gamma will darken it. So I'll just assume that the gamma is equal to 2. What is the meaning of that? I'll get S is equal to constant, I'll take it as 1, R to the power of 2, R square. So if I directly use this type of monitor, you will see a dark image here. Now what I'll do is I'll use the gamma correction. So this is a gamma correction block. Okay, so what I'll do is I'll raise s to the power of 1 by 2. So let me call this as say some t. What happens? S to the power of 1 by 2, and s is actually r square to the power of 1 by 2. So 2 cancels, I'll get r. Do you notice what has happened? Any question here or doubt?
Yes, yes, sir.
So this block is by using image processing. So this is called gamma correction, where I will just correct for any brightness aberrations in an image. That's exactly what is shown here. So you have a linear wedge here. You have a monitor, faulty monitor, which is going to give you an image which is darker. And to correct for this aberrations in the monitor, I'll first do gamma correction. That's exactly what I have done. I've done that gamma correction here. That means whatever constant you have, the reverse of that I have done here, so that I'll get back my original image. That means the monitor problem is corrected by using this gamma correction. So this is, so I don't need to throw such type of monitors which are giving display aberrations. I can use a simple technique called gamma correction. Okay, this is the application of power law transformation. Okay, so this is an example. Please understand what is being done here. I think the story is written here. This is an MR image of a fractured human spine. Okay, uh, you can see that most of this region is not visible. Okay, so if you just use different values of gamma 0 0.6, 0 0.4, 0.3, so just observe 0 0.6, 0 0.4, 0.3. So if I go up, that means I am brightening the image. So notice that this region is being brightened. Do you see? Some information which was not at all visible here is visible here. So I can use this type of transformation techniques to brighten a given image. I think this you can also try by yourself. You can just capture some image when the light is very dim in your room, maybe the lights are off, then pass it through a simple power law transformation like this to brighten it. The image gets brightened. Okay, so this can be tried by yourself. Okay, so this is power law transformation, which is one of the pre-processing step that we normally do whenever you want to. Okay, for example, a license plate image. I want to detect the license plate. The vehicle has entered somewhere in the evening, late in the evening, so the illumination is very less. So the image is captured, but the intensity is not good enough. So I can brighten it by using pre-processing and then pass it to the rest of the circuitry or the rest of the blocks to identify the license plate. So many such applications are possible. This is another example where you can see that this is a bright image. Okay, the image you can see it looks very dull because most of the pixels are bright. And if I use gamma 3, 4 and 5, observe gamma 3, 4 and 5 means I'm going towards the darker side. So a bright image is being darkened. So probably this would be a better representation of the image compared to this. Okay, so let me just probably go to the, yeah. So this is a bright image which I have darkened by using power law transformation. Okay, so this is how I can use power law transformation to correct for brightness variation or illumination variations. Now let us assume that I am interested in, okay, something like this. Assume that I am interested in a transformation something like this. This is or this is yes. See in the logarithmic transformation, in fact in negative, I had a very nice equation L minus 1 minus R, so I could easily implement it. in logarithmic transformation, I have a very nice equation S is equal to C into log of 1 plus R. I could easily implement it. In power law transformation, I have a very nice equation R to the power of gamma. So I could implement this. All these are implementable. Now if I need something like this, assume that for one of the applications, the dark pixels should be darkened, the bright pixels should be brightened, and whereas I want almost a linearity, something like this. If you carefully observe, something like this. But I don't have an equation for this. I cannot fit an equation. Very difficult to fit a nonlinear equation for this. So in such cases, what we do is we use what is known as a piecewise linear graph. Hopefully remember, when you are approximating your diode as a linear circuit, you use this. So what we do is I'll just fit a linear curve here approximately. So this is the first portion. For the second portion, I'll just fit a linear curve here, something like this. For the third portion, I'll fit a linear curve here. I hope you understood what I have done. So this is linear here. The next part, it is linear here, and the next, that means a nonlinear curve is being approximated using what is known as piecewise linear approximation. Piecewise linear approximation. Okay, so whenever I want to have an arbitrary transformation function like this, it's always better to use, because it's very difficult to represent this by a nonlinear equation. So approximate it by piecewise linear approximation. So that's exactly what is being discussed now. Okay, so the reason, because it is practically implementable, so it's easy for me to use such piecewise approximation and implement it. Is it difficult to implement this? No, because for example, assume that this value is 10, say maybe this value is some 150, and this value say some 255, and assume that maybe this value say some 5, and probably this value say some 200, and this value say 255. So I can use for loop. For all the gray level values from 0 to 10, I'll use this slope. For all the gray levels from 10 to say 150, I'll use this slope. And for all the values from 150 to 255, I'll use this slope. So I can make an approximation and use what is known as a piecewise linear graph. So it is practically implementable. Many nonlinear transformations are approximated like this. And in fact, one of the good example is contrast stretching, which will stretch a low contrast image normally captured because of poor illumination, and because of this the dynamic range will be in fact very narrow, and this could be even because of the image sensors, or sometimes even the setting of the lens aperture is not good. So I can use this type of transformation. So it is, the slope is constant here, the slope is constant here, the slope is constant here. So a good example is shown here. For example, if I have an image of this nature, a low contrast image, then by using contrast stretching, I can just use some such things and separate it like this. Now you can see this image is much better than this image. Do you notice? You can see some information here. Now maybe after this, if I just do some thresholding, where anything above some level is white and below that level is black, I can see some black and white values, which would help me in probably, okay, doing some segmentation or separation of these things. Okay, so this is how a piecewise linear transformation works. It is a piecewise approximation to a nonlinear curve, and you can have many such slopes. Okay, this is only an example. Okay, so probably I will stop at this stage. This has to be discussed in detail, so we'll take an example and discuss. I just want to spend some time on your test question paper, so let me just stop at this stage.